more. There, that's... Okay, so I'd like to speak about, well, not exactly discrete, but I prefer actually to change the title to quantum Riemannian geometry and gauge theory. So one interesting thing about this period in the history of mathematics and physics is that everybody is struggling to come up with a new concept of space or space-time. And there are lots of different directions being explored right now, and it's very nice to see that lots of them are being represented at this conference. So the concept of graph, of course, is a very nice primitive combinatorial notion of space. And we've seen talks about combinatorial approaches to Riemannian geometry. We've seen ideas about supermanifolds, and lots of other ideas are being explored, like non-commutative geometry and so on. And from my point of view, there's a good reason why right now everybody's struggling to make up all these new ideas about space and time, and that's because we don't really know what space and time are like, and all we know is that everything we know must be a little bit wrong. Basically because of two things, general relativity and quantum mechanics. So special relativity unifies space and time, but general relativity is much more deep and interesting because it says that the geometry of space-time is not a pre-established fixed thing upon which events play out, but in fact the geometry of space-time is a dynamical variable in terms of physics. That is, it's something that interacts with the stuff in space-time. It pushes them around, but they also push it around. And so ultimately, if you carry that line of reasoning out long enough, you start thinking that maybe the geometry of space-time doesn't really have a privileged role over the other dynamical variables in the theory. And in a theory like string theory, for example, the metric is just a tiny tip of the iceberg of what's going on. But on the other hand, we know from quantum mechanics that everything is uncertain, or more precisely, for every quantity you might want to measure, there's some other quantity you might also want to measure, such that you can't know both of them precisely at once. And that must apply to the geometry of space-time as well. And so that means that the ordinary concept of, say, a Lorentzian manifold can't possibly be what we really use to describe space-time, because there's no uncertainty in that. It must be replaced by something more quantum mechanical, and no one knows quite what that is. So right now people are fumbling around, coming up with all sorts of beautiful mathematics in an attempt to hit upon something that will work better. So I'd like to talk about some ideas that people have developed to tackle these problems, and I should emphasize that these are just, from the point of view of physics, just one of many different ideas, but there's some real mathematics here too, so even if the physics turns out to be wrong, as it probably will, like all the other theories we have right now, the mathematics may remain. So here's my plan. In the first talk, I'd like to say a little bit about why quantum gravity is so hard, why it's so hard to combine quantum mechanics and general relativity. To go into that a bit more, I have to focus on some particular approach to quantum gravity, because there are really as many answers to the question why quantum gravity is hard as there are approaches to quantum gravity. Every different approach, you need some dragon or other on your path, and sometimes they are just different disguises of the same problem, but I have to pick something particular to say anything specific. So I'll be talking about what's called non-perturbative canonical quantum gravity. I'll explain those terms. And there the problems have to do with constraint equations. So I need to talk a bit about constrained systems, classical systems, and quantization of constrained systems. And then I'll turn to Einstein's equation, the basic equation of general relativity in particular, and show you how the constraints show up there, and say a little bit about some early naive attempts to quantize those equations and the difficulties that you run into when you try to do that. And then I'll talk a little bit about some new ideas, the so-called Ashtekar new variables and loop quantization, which I think is a pretty interesting approach to try to get around some of those problems. But I won't say much about that in the first talk. Then in the second talk, I'll introduce some mathematical machinery. I'll talk about doing gauge theory not on a manifold, but on a graph. And I'll show you how spin networks, certain combinatorial objects built up out of graphs and representation theory, I'll show you how those naturally arise when you're doing gauge theory on a graph. And then I'll show you how you can use that technology to study gauge theory on a manifold. And I'll focus on a real analytic manifold for technical reasons, which you'll see. Then in the third talk, I'll return to the original problem of trying to quantize gravity and explain in more detail what these new variables are for describing general relativity. And the point is that in those new variables, all this technology becomes useful for trying to quantize gravity. And so I'll show you how we apply that technology, and then I'll begin to sketch some results, so to speak, physical predictions that you get from this approach. And the two main results I'll talk about are, first of all, the quantization of area, which I mean in a rather literal-minded sense, that if in this model, if you measure the area of a surface, it can't take a continuous range of values. There are certain discrete values that the area is allowed to assume. So in other words, there's an area operator which has certain eigenvalues, which are the allowed areas. And then second of all, the non-commutativity of area operators. Another, perhaps even more curious feature of this theory is that if you have two surfaces that intersect, their area operators don't commute, meaning physically that you can't know the areas of both of them precisely at once. There's no state in which both of them have precisely defined areas. And then, well, then for my fourth talk, but I should say that about these physical consequences, Abai Ashtekar will give a talk on the last day of the conference and go into a lot more detail about the physics of the applications to physics of these ideas. So the two places where we know that our concepts of space-time must break down are the Big Bang, this initial singularity at the beginning of the universe, so to speak, and the black holes, through which many stars are doomed to become. So there, if you follow general relativity, you find that the curvature becomes infinite as you approach these singularities, and that's a pretty sure sign that something is going wrong. We'd expect that at very high curvatures, quantum effects would become important. So the two places where quantum gravity is, so to speak, staring us in the face are the Big Bang and black holes, and he'll talk about some applications of loop quantum gravity, some recent ones actually, to studying those two physical topics. So basically, I'm setting up some mathematical machinery, and then he'll be able to take advantage of that to do some interesting physics. And finally, I'd like to talk about some ideas that I'm very interested in called spin foams, which are a combinatorial approach to the study of space-time. Most of this, from the point of view of physics, will be about space rather than space-time, but spin foams for sort of time gets into the picture. So that's my plan. Okay. So why is quantum gravity hard? Or more precisely, why is canonical quantum gravity hard? Well, I need to say what canonical quantum gravity would be. For starters, I will be talking, just to keep things simple, only about the vacuum Einstein equations, the equations where there's just a metric around and no matter. Nonetheless, things can be pretty interesting. So the vacuum Einstein equations say that this certain tensor, the Einstein tensor, vanishes. So here's the setup. You've got a three-manifold representing space, and I'll have it be a compact, smooth three-manifold to keep some things simpler. And space-time I'll just take to be r cross s. So I'll often parameterize r by this number t, which is just time. And then our basic field in general relativity is a Lorentzian metric on this manifold m. And since we're doing canonical quantum gravity, we want to restrict the situation so that this surface, say t equals 0, which is a copy of S sitting inside M, is a space-like surface. So the metric restricts to being a Riemannian metric there. And in fact, we want something a little more strong than that. We want it to be what's called a Cauchy surface, basically meaning that you take any point in space-time and you take any time-like path through it, it's bound to hit S. And also there are no closed time-like curves. So those are some technical conditions. But anyway, starting from this metric, you can form first the Riemann tensor, then by contracting two indices, you can form the Ricci tensor, R mu nu. You can form the Ricci scalar by further contracting that. and then r mu nu minus 1/2 r g mu nu is the Einstein tensor. And for certain reasons, which I won't try to explain right now, it's a very good idea to study that tensor. And Einstein says that if there's no matter around, that tensor is equal to 0. So what would quantizing this system of equations mean? So I'm very often confronted by mathematicians who ask me, what is quantization anyway? What's quantizing? And I always feel at a loss to give a short, snappy answer to that, because actually quantization is a lot like cooking. And so if you're asking me what's quantization like, or how do you quantize, it's sort of like coming up to me and saying, okay, how do you cook? And I can give you an abstract general answer, which would be sort of something like, well, you take raw ingredients and you transform them into something that you want to eat. and that's true, that's what cooking is all about. But that doesn't really give you much of a feeling for how you actually go about this process. And so if I wanted to be more specific, well, I'd have to say, well, there's baking, there's boiling, there's frying, there's sautéing. There are all sorts of sophisticated techniques and tools that people have devised for this thing called cooking. And, tell me one kind of cooking you want me to explain to you, and I'll do it for you. But of course, the real way to learn about cooking is to actually try it sometime. And that's pretty much the same way it is with quantization. You just have to start trying it. And so there's no quick and easy answer to this question.
What the analog that you're thinking, transforming long products?
Okay, well, transforming a classical theory into a theory that has a chance of being true because it is quantum, meaning that the uncertainty principle applies there. So that's about as vague as the other thing, right? So you have to have different people have different things that they want to eat, and different people have different things that they want to do when they're doing quantum mechanics. So there's some fair amount of flexibility in that definition. Certain into uncertain. Well, yeah, but that sounds fairly negative, right? Yeah, transforming the certain into the uncertain.
The final product has to have some kind of resemblance at least.
Right, that too, and that's also true for cooking, right? Yeah. It's any good, yeah. Okay, but you see, to get a little bit more specifically, we need to focus in on some approach to quantization. So, in quantum gravity, we have this space of solutions of this Einstein's equation, and that we would like to make into so I'm going to now pick an approach, and I'm immediately eliminating many different perfectly fine approaches to quantization when I start talking now about this one. We're going to try to make that thing into a Poisson manifold. That is a manifold on which the functions form a Poisson algebra. So does everyone know what a Poisson algebra is? Does anyone dare admit that they don't know what a Poisson algebra is? If someone dares admit, then I can tell you. Okay, he knows what he'd like to hear. Yeah, okay. So a Poisson algebra is a commutative associative algebra with unit, together with a bilinear operation called the brackets, which makes this algebra into a Lie algebra as well. Don't ask me to define that, or I'll be stuck in a recursive sequence of definitions, such that bracketing with any one particular element, if you think of that as a map from the algebra to itself, that's a derivation. Or in other words, f of gh is f g h plus, say, f h g. So in the case of a Poisson manifold, A is going to be, the smooth functions on your manifold, and then, of course, derivations of smooth function of the algebra of smooth functions are really just vector fields. So it's saying that to any function we can associate a vector field, and these vector fields naturally form a Lie algebra. So that's a Poisson manifold, and I can't really explain why people have, over the course of a century or so, realized that classical mechanics has a lot to do with Poisson manifolds. I'll give some examples that will do better at explaining that. I'll give you the prime example in a second. Yeah. So then what we would like to do with this Poisson manifold, once it's a Poisson manifold, we understand the system classically. Then we'd like to quantize it. I'll say more about what that means. And in canonical quantum gravity, the way we describe these solutions of our equation, Einstein's equations, is using initial data, that is, using fields at time zero, on this time zero slice. So for some silly reason, canonical means that you make this completely non-canonical choice of a particular space-like slice, and you use that to describe your solutions. A Poisson manifold is a manifold whose algebra of smooth functions is equipped with this bracket structure satisfying these axioms. So let me say a little bit about some examples here. So there are lots of tricks for quantizing Poisson manifolds, but let me start with an example of a Poisson manifold. The simplest classical system, perhaps, is a particle moving along on the real line. We describe its state, that is, the way it is, by specifying its position and velocity, or if you prefer, and I do, its position and momentum, its mass times its velocity. So if you describe it by a pair, Q, P. To confuse non-initiates, we use P not to stand for position. That's just so that outsiders can easily be detected. So the sophisticated way to think about this space of pairs is to think of it as the cotangent bundle of the space of positions. So R is the space of positions here, also called the configuration space. But a cotangent vector would be the momentum. And this, like any cotangent bundle, it's a Poisson manifold. In fact, it's better than that. It's a symplectic manifold. But as a Poisson manifold, I just need to tell you what the Poisson brackets of functions are. And in fact, I really just need to tell you what the Poisson brackets of these basic functions, Q and P, are, because then you know from those rules what the Poisson bracket of any polynomials is. And then by a kind of completion process, you can work out what the Poisson bracket of any pair of smooth functions is. So these just have to be zero because it's a Lie algebra. So the only interesting thing really is that P and Q satisfy that their brackets are 1. So there's some kind of structure that comes along naturally when you have a cotangent bundle, which in this particular case says this. So these are called the canonical commutation relations, and that's actually the real reason for this, these are canonical Poisson bracket relations, I guess. That's really the reason for this word canonical. So we have this Poisson manifold, and to quantize it, what we would like to do is we would like to find a Hilbert space on which there are operators whose commutation relations mimic those Poisson bracket relations. And the way that Schrödinger did this in the first place was he said, I'll take my Hilbert space to be L2 of R. So a state of my quantum system, that is the state of a quantum particle on the line, will be a unit vector in this Hilbert space. And then I can describe position and momentum by certain self-adjoint operators on this Hilbert space. And what they are is just multiplication by the function q, so that's the multiplication operator on here, and 1 over I, or really h bar over I if you include Planck's constant explicitly, times the differential operator, ddq. So they're just multiplication and differentiation. Their commutator is 1 over I. The commutator p bar and p hat and q hat is 1 over I, and that's basically what I mean by mimicking this relation. This 1 over I comes in just from the fact that we want to work with self-adjoint operators, so we have to divide by I there. And of course those relations also hold if you stick hats on them. So we say that we have quantized when we've gotten ourselves this Hilbert space now with these operators on it, satisfying these kind of relations. The point being that most of classical mechanics can be done using just those Poisson bracket relations. And so we can copy now a whole bunch of stuff in this quantum situation using these operators. So that's the simplest kind of quantization of all, the kind you learn when you're starting out learning about quantum mechanics. And a naive approach to quantum gravity would be, okay, I want to do this same thing, but now not starting with the cotangent bundle of the real line, but starting with the space of solutions of Einstein's equations. So that turns out to be a lot harder for a number of reasons, and so let me quickly tell you those reasons, and then we'll see them in more detail later. So first of all, obviously if you've thought about differential equations, the space of solutions of Einstein's equations is going to be some infinite dimensional thing. So a lot of problems of analysis will come in. In particular, it's not so easy to define L2 of an infinite dimensional manifold. Second of all, it's not even a manifold. The correct phase space for Einstein's equations is not a manifold. It's a quotient of a manifold by something like a group action. And so it has a lot of singular points. So it has singularities as well. Next, the problem is that the phase space, that is this, the space of solutions of Einstein's equations, or the thing that's analogous to this, we call it the phase space, the Poisson manifold, it's not a cotangent bundle. We'll see that that comes from the fact that Einstein's equation has certain constraints on the initial data put in. Einstein's equations include some equations that are constraints on the initial data. So I need to talk a lot about constraints to understand this. And third, there's a problem which is both mathematical and also philosophical, somewhat philosophical, in that the real Poisson manifold that you should be trying to quantize is not the space of solutions of Einstein's equations. It's the space of solutions of Einstein's equations modulo diffeomorphisms of space-time. The point being that if we did a diffeomorphism to this room, none of us would notice the difference. So as an actual physical situation, it would be the same. Yes?
The space of solutions of Einstein's equation rather than the space of all vectors.
Well,
Could you repeat it, buddy?
yeah. So he asked, why am I trying to work with the space of all solutions of Einstein's equations instead of the space of all Lorentzian metrics? Well, one way to answer that question is by analogy with this example. So in this example here, I described it in terms of the position and momentum of a particle at a specific time. But if I actually had some particular equations that I was trying to quantize, say the equations for a free particle that says that the particle just marches along at constant velocity, then what I really would be doing here is quantizing the space of solutions of that equation. So the space of solutions of the equation for a particle marching along at constant velocity is just the same, or isomorphic, T star of R, because if I know the particle's position and velocity initially, then I know the solution. So in fact, the first answer to your question is we're always trying to quantize the space of solutions of our equation. So it's nothing special about Einstein's equation. That's one answer to it. And then the problem is, how do you parameterize or describe the space of solutions? Well, there are different ways to do that, but in most complicated cases, the only way you can get your hands on that we know so far is in terms of initial data. That's in terms of what's going on at a specific time. So you should really think of these as the position and momentum of the particle at time 0. And over here, we'll be eventually describing solutions of Einstein's equation in terms of some stuff going on this T0 slice, the metric, and roughly speaking, the first time derivative of the metric. So the space of all Lorentzian metrics is a much bigger thing, and that doesn't have any strong relation. I mean, it has some relation, but it doesn't have any strong relation to Einstein's equation. So you could try to put a Poisson structure on that and quantize it, but you wouldn't be quantizing Einstein's equations. You'd just be quantizing the theory of a Lorentzian metric, an arbitrary Lorentzian metric, and that would not be, well, you wouldn't be able to get any of the stuff, like black holes or anything, out of that. Well, in the path integral approach to quantization, which is a
Can you repeat the question, please?
He was just sort of saying, well, in the path integral approach to quantization, you do consider all for example, all paths of a particle are all Lorentzian metrics. And that's true. That's just a different approach. And it's not at all supposed to be obvious a priori why that approach winds up being related to this one. When Feynman first invented his path integrals, all the old fogies, all the glorious old people of quantum mechanics thought that his approach had to be wrong because he was talking about specific paths of particles, and they had just proved shortly before that you couldn't know the position and momentum of a particle simultaneously. So it's a subtle isomorphism that's involved to translate between that path integral approach and this one. So I'm not going to try to explain how that approach winds up being equivalent under favorable conditions to this one. But you should also always worry, are these different approaches to quantization going to wind up giving me fundamentally the same answer? Sometimes they do, sometimes they don't. Everything that can possibly go wrong does sometimes go wrong in this game.
In the case of something of quantitative random answer, space-time slices, that's a good idea to identify the solutions with the initial conditions, because this slice is clearly a variant in the first place. But just in this original formalism, it seems like you even gears and variational point to have the classical path, then you have these variation principles, so you also sort of nearby path as far as which sort of relation aren't in the solution space.
Yeah. So you're saying that, well, you're just saying that that same mystery, how does considering all paths wind up being related to considering only those paths that are solutions? You're saying that same mystery is already sort of working in the classical problem when you're doing variational calculus.
Well, I guess the mystery for me is I still don't see breaking the line in this general setting. On geometry, solution,
Well, I don't know if I'm...
John, will you please repeat the question?
He's just wondering, why am I trying to quantize this space of solutions? Well, you've just been exposed to too much path integral quantization. That's all I can say. So you have to bridge the gap between that approach and this approach and see that at least when things are working out nicely, which is a large number of realistic situations, you can do it both ways and you get the same actual physical predictions, even though the calculations superficially look completely different. So I'm not going to try to explain that. That would be like a whole talk. Why is path integral quantization the same as canonical quantization? I'm just going to explain canonical quantization. Yeah?
But at least when you write down these equations, there is some Poisson structure.
We're going to get a Poisson structure on the space of solutions. Okay, you're supporting me? Good. Okay, I'm all in favor of that. So yeah, we're going to get ourselves a Poisson manifold of solutions of Einstein's equations modulo diffeomorphism. So even if you don't believe in quantum mechanics or any of this baloney about quantum mechanics, you know, that's something actually about purely classical, and that's what I'm mainly going to talk about. So anyway, there's this thing called the problem of time, which is that you really are only going to get the phase space for general relativity when you look at solutions modulo diffeomorphisms, and that is very different from what we're used to in normal physics, that is physics that does not take general relativity into account. In normal physics, time translation acts on the space of solutions, but you don't mod out by it. So you are able to describe time translation as a group action on this Poisson manifold, and then when you quantize, as a group action on this Hilbert space, and that's the main thing you try to do in physics, is to figure out what's going to happen in the future given what's going on now. You use this group action to do that. In situations like general relativity, that is sort of ruled out from the very start because you've modded out by all the diffeomorphisms, and people have struggled around that problem for a long time. So those are some difficulties. Let me say a little bit about quantizing constrained systems as a warm-up for general relativity. So let me do the simplest example of a constrained system. So suppose you have a particle on a plane, but then you constrain it so that it actually lies on, say, the x-axis. So classically, the particle on the plane is described as follows. We have this configuration space, that is the space of possible positions, or q's, and that's just the plane. Then the phase space, the space of positions and momentum, would be the cotangent bundle of R2. So it's just like what I said before, but now with R2 instead of R. So it would be a four-dimensional space, and it would be a Poisson manifold with these Poisson brackets. So the q's commute, the p's commute, but the p's and q's don't. You get this Kronecker delta in their Poisson bracket. And then, of course, we can quantize this system, just like I did for the particle on the line. So now the Hilbert space is, again, L2 of the configuration space. So it's L2 of R2 now. And we get four interesting fundamental operators on it. Two position operators, multiplication by Q1 and by Q2. Two momentum operators, differentiation in the Q1 and Q2 directions divided by I, whose commutation relations will mimic these. So if you just put hats on these equations and turn the Poisson brackets into commutator brackets, stick a 1 over I here, then you get the equation satisfied by these operators. Okay, so that's the quantum mechanics of a particle on a plane. Now suppose you said, I don't want to think about a particle that's just freely able to move on the plane. Suppose there's some extremely strong force on it, or some rigid thing grabbing it that makes it so that it can only move along the x-axis. So it's really a particle on the line. Well, of course, in this simple example, you could just say, well, then throw out all this stuff, go back to the previous transparency and work with that. But what we want to do is not that. We want to see how, from this description, we can impose this constraint that the y-coordinate, that is Q2, is 0, and get back to the previous transparency in some fairly systematic manner. So there are two kinds of routes that we can follow here. We can try to do this constraining business at the classical level, at the level of the classical description, or we can try to do it after we've quantized. So let me quickly sketch how both of those routes work. So classically, the phase space of the particle on the plane is the cotangent bundle of R2. We know the answer that we're trying to get to. We're trying to get back to the cotangent bundle of R as the phase space for a particle on the line. So basically, we need to somehow justify chopping out these two dimensions to get down here. Well, one of those is easy to justify. The constraint Q2 equals 0 will pick out a three-dimensional submanifold of this. But there's some further finagling to be done because we somehow also need to forget about P2, the momentum in the second direction. Now, you could say we're also going to set that equal to 0. That would be one way to say it, but it turns out a more precise way to say it, which we'll see why it's more precise in the next transparency, is just better to say instead of constraining it to be equal to 0, we will think of modding out by it. In other words, ignoring it. That is, saying that P2 will now be treated as the same as P2 plus any constant. So this process of going from here to here, it's best not thought of as picking out a subspace of the original space. And if you know enough differential geometry, you know that it's not really natural to think of this as a subspace of this. Instead, there's a kind of two-step process going on where we first pick out a submanifold, and then we take a quotient space of that to get down to our physical our phase space here. So that two-step process is called Poisson reduction. You may know the more specific example of symplectic reduction, but this works in pretty much the same way, and I'll talk about it in a minute. And that's the way you constrain systems classically. I need to explain it in general, but that's what it does here. Over at the quantum level, it's interesting. It's not a two-step process. It's a one-shot process. So we started out with this Hilbert space of functions on the plane. We're trying to get the Hilbert space of functions on the line. Naively, what we do is we look at not all functions in here, but only those for which this constraint holds. That is, all functions such that Q2 hat, this operator applied to them, equals 0. That, naively, will pick out a subspace of this original Hilbert space, which will be L2 of the real line. So now we have functions that basically are just living on the x-axis. So who sees why I've been saying naively the last couple of times? Okay, you do. Yeah, so if you have a function in L2 of the plane, which is supported on the x-axis, it's 0 almost everywhere, and so it's actually 0 as an element of L2, because L2 consists of equivalence classes of functions, modulo being equal almost everywhere. So in fact, this is not really a subspace of this. There's some technical work that needs to be done to justify the extraction of this Hilbert space from this space. So another way to say it is the problem is that this operator here has a continuous spectrum. If it had a discrete spectrum and it had some 0 eigenvalues, you could pick out those corresponding 0 eigenvectors, and that would be this. But when your constraint is an operator with a continuous spectrum, you have to use sneakier methods to justify this process. So I won't try to get into the analysis of that. I'll just say, for now, that this tells you pick out functions that are supported on the line. It's up to you how to make them into a Hilbert space. There is a best way to do it, and if you do it that best way, you'll get L2 of the real line. So that's an example of the analytical technicalities you get into when you try to go do this stuff right. Let me say a bit more about Poisson reduction, though. So the idea here is that we're going to start with a Poisson manifold, X. I'll call that the kinematical phase space. It's the phase space that we start out working with, but we're just using it as a stepping stone towards getting a more interesting Poisson manifold. And then what we're going to do is we're going to impose a constraint that f equals 0, where f is some smooth function on this Poisson manifold. So we're going to try to get a new Poisson manifold in the end from that data. And we do this two-step process that I already alluded to. First, we pick out a subspace of X. If we're lucky, it will be a submanifold, which is just called a constraint surface with points where f equals 0. That will hardly ever be a Poisson manifold in its own right, as I'll soon explain. So you can't usually stop there. You usually have to do this next step of taking a quotient space by a certain equivalence relation. That will be a Poisson manifold, and that will be what we call our physical phase space, the phase space we were really after for describing our system with this constraint that f equals 0. So what's this second process? Well, it works like this. You take your function f, Poisson bracketing with it is a derivation of our algebra of smooth functions, so in other words, it's a vector field. So associated to this function f, we got a vector field, v sub f, on our manifold X. And that vector field, if we're lucky, will generate a flow. Of course, not all vector fields are integrable. They don't always generate flow. So you can see we have to have some luck at various stages of this procedure to get it to really work. So suppose it generates a flow, f sub t, from x to x. So for any... Well, we started out being in the smooth category, but the solution set of a smooth function doesn't need to be a smooth manifold, and not every smooth vector field generates a flow. So we'd like to stay in the smooth category, yes, but we have to have the force with us to be able to remain there. Yeah. Okay, it may not last for all time. It's a short-lived flow. Yeah, I guess that's probably good enough for what we're trying to do. Yeah, okay. So for any particular point x, there'll be some interval of t's for which this is defined, partially defined. Okay, so you're trying to push the limits of this thing. Okay, that's fine. So that's usually not the worst problem that happens here, as far as I know. Usually the problems happen with this thing not being submanifold. That's very common. Okay, so so even if it's a short-lived flow, it's enough to allow us to define this equivalence relation, the 2 points related by that flow for some t, for which the flow is well defined, are discrete equivalent. So we mod out by that equivalence relation. And if we're lucky, this will be a manifold. Again, often it won't. Often now we'll be pushed over into working with some kind of orbifolds or varieties or something like that, because there will be often singularities coming from the fact that this flow doesn't need to act freely on this constraint surface. So, to see why this thing is again a Poisson manifold, if all these nice conditions have been met, it's best to just go over here and think not about the spaces, but to think about algebras of functions on the spaces. So the old trick of going from geometry to algebra, and think about what Poisson reduction looks like over in that viewpoint. So we started out with this Poisson algebra of smooth functions. We call them observables. A function on phase space assigns to each point a number. That's what you could observe that quantity to be at that particular state of the physical system. So these are observables. We call them kinematical observables because this is just the preliminary kinematical phase space. I'm just trying to teach you some physics jargon here along the way, so that you can understand when actual people talk about this stuff. So the process of going to this subspace of X corresponds, of course, to going to a quotient algebra of C infinity functions. So we mod out by the ideal generated by F. And then this process of quotienting the space naturally corresponds to going to a subalgebra of that. So what we actually are doing, if you ponder this carefully, is we're picking out the subalgebra of this algebra, which is just described as follows. We take all the smooth functions which commute via Poisson bracket with F, that they will form an algebra because this relation here says that if G and H commute with F, so does their product. So this is an algebra, which is a subalgebra of the smooth functions, and we mod out by that same ideal. So this, you can see, naturally inherits a Poisson bracket from the Poisson bracket on here. So in other words, you need to check that if you have two elements of this quotient algebra, pick representatives of them, which are smooth functions, take their Poisson bracket, and that will be well-defined modulo this ideal. Basically just because, again, of this equation over here. So with this thing, has a good chance of being a Poisson manifold, because the algebra of functions on it is a Poisson algebra. Notice that this algebraic stuff, in a sense, is simpler than this stuff here, because we don't need to be talking about manifolds, we don't need to have submanifolds, we don't need to have a free action. We could just do this for any Poisson algebra and any element of it. So actually, when you're trying to really do this stuff, it can be often more convenient to work not with these phase spaces, but with these algebras of functions on them. So that's Poisson reduction in a nutshell, and there are lots of nice theorems about it, especially in the case when your manifold is symplectic. Sometimes it's called Marsden-Weinstein reduction because they were among the people who did it in that symplectic case, but it had been implicit in the physics literature even before then. So this here is a situation where we're taking a single function and we're imposing that as a constraint, picking out this constraint surface and then modding out by that. But we could also do it when we have a bunch of constraints, there's a bunch of functions, and it works out most nicely when those functions actually are a Lie subalgebra of the algebra of functions on your manifold, because then they, with any luck, will generate a group action, and then you can mimic this whole story, but instead of getting this action of R on your phase space, you get an action of the group generated by that. So Poisson reduction works reasonably well when you have functions that form a Lie algebra. But as usual, that's not everything that can go wrong does, and so actually in general relativity that will not be the case for the constraints that you're trying to work with. Okay. Let me now turn over to general relativity. So I said I was going to try to describe solutions of Einstein's equations in terms of their initial data on our space-like slice, S. So here's our space-time manifold R cross S. Here's S, that is this t equals 0 slice. I've drawn it curvy because I'm trying to indicate there's some curved geometry going on here. And we're trying to describe solutions of Einstein's equations in terms of fields, the metric and its time derivative and so on S. And it'll be very convenient to pick a time-like unit normal vector to S called n. And I'll be writing down some formulas with indices, and those indices will be basically working in a local coordinate system on S, which I'm thinking of as a 3-manifold here, so those will go from 1 to 3. All these formulas that I'm writing down, you can sort of let your eyes glaze over when you look at them, because we're not really going to use the details of these formulas. I'm just writing them down so you know that this stuff is real, that it really exists. Okay, so we're going to start out with the space of all metrics on S as the analog of the space of all positions of our particle. So the space of all metrics on S, if you put a few qualifiers in there, becomes an infinite dimensional manifold. You could work with smooth metrics on S. You could work with metrics in some Sobolev space. I don't want to worry about those technical details here, but I'll be glad to try to answer questions like that if you have them. But let me not worry about analysis. So let's just say the space of all metrics on S will be our kinematical configuration space. That is the configuration space we start out with before we start worrying about any constraints. I'll call a metric on S Q, because that's analogous to the position of the particle in the earlier examples. The kinematical phase space will just be the cotangent bundle of that infinite dimensional manifold. So it will consist of pairs of a metric and some cotangent vector. But now you should ask me, what's the physical meaning of this cotangent vector in this case? Before, in the simpler example, it was just the momentum of our point particle. Now, it's something cooked up from the extrinsic curvature of S as it sits inside M, our space-time. So there's a tensor on S called the extrinsic curvature, which you get just by taking the covariant derivative of n in one of these directions along S and see how n tips over, so to speak. See how it becomes no longer orthogonal to S. So that's what we're doing here, really. We're taking the covariant derivative of n in some direction and then taking one of the spatial components of the result. That's called the extrinsic curvature. And P, the thing that's analogous to momentum in general relativity, is cooked up from that and also from the metric on space. So I'm not deriving this formula, I'm just dropping it on you. But one can, from certain other approaches, derive it. So you'll notice there's some nasty stuff. There's the square root of the determinant of the metric showing up here as well, which turns out to be a technical problem in some situations. Yeah?
Since you have all your metrics on S, why can't you take a current derivative of this normal metric?
Well, to define any of this stuff here, I need more than just a metric on S. Up above this line here, between here and here, all I needed to know about was metrics on S. And I can certainly talk abstractly about these cotangent vectors without thinking about the whole space-time. But to understand how we're going to apply these cotangent vectors to the physics problem at hand, I need to now say, let's suppose we actually had not just a metric on S, but a metric on the whole space-time. Then I can tell you, sort of whisper in your ear, what I'm going to use P for, and it will be basically this extrinsic curvature thing, which can only be defined if you have a metric on the space-time. Yeah? Uh-huh. Yeah.
As such, it would have intrinsic cotangent bundle.
Sure.
Here it looks like you can start the cotangent bundle as something that depends on this embedding this thing in this.
Right. Well, I think it's sort of the same question. I'm sort of saying above this line, we don't need to think anything about an embedding of, we don't need to think about an embedding of S in the space-time or anything. P is certainly well-defined. It's just a cotangent vector to this manifold. But it's just, think about, again, the example of the particle on the line. So Q, the position, tells you where on the line. You can say P is just a cotangent vector to the line. And that's fine. But if you're going to do physics with that, you want to know something about why the heck do I care about a cotangent vector at that point. And so then I need to whisper into your ear, that's momentum, and momentum is mass times velocity. And velocity involves the time derivative of q. So for you to understand all those sentences, you need to think not just of the particle at that specific time, but of what it's doing at other times. So similarly, to understand all this stuff, which is the exactly analogous stuff, you need to think not just about the metric on space, but actually the metric on space-time that we're going to study via this. So we're aiming, remember what we're aiming for. We're aiming for a description of the space of solutions of Einstein's equations.
If you get this way, it appears that those three lines are part of the definition.
Yeah, okay.
Okay.
So I should have stuck an extra word here, like secretly, right? Meaning that it's not part of the definition of P, it's what we're going to use P for. Yeah.
It's a choice of quantization.
No, it's a choice of what we're going to do with this cotangent vector, how we're going to identify. When we get around to describing solutions of Einstein's equation using P and Q, the role P will play is it will be a description of the extrinsic curvature. Yeah, just like the momentum is a way of talking about mass times velocity. Yeah, so I'm sorry. Yeah, this stuff here is sort of logically separate from the rest of the transparency. So the Poisson brackets on the cotangent bundle of the space of metrics, they can be defined without knowing any of this stuff, of course, because you always have Poisson brackets of functions on any cotangent bundle, and they always work the same way. This is how physicists and indoctrinated mathematicians write those things in an abbreviated manner. It's a somewhat disturbing formula if you're not used to it. So here, Pij is really this, we're thinking of it as taking a value at any point x in S. It's a field, in other words, it's a tensor on S. And so is Q. And I'm taking the Poisson bracket of those two quantities. Those two quantities are certain functions on P star of met S. And I'm writing down their Poisson brackets. There's some Kronecker deltas, which are not disturbing, but there's also a Dirac delta, 0 unless the points x and y coincide. And that, of course, is disturbing, because that could be either 0 or infinity. So what this formula really means is this formula doesn't make sense unless you smear with test functions. You should really integrate over some function of x times some function of y times this stuff. Then this is well defined. So in other words, these functions on the cotangent bundle are a little bit too nasty to have well-defined Poisson brackets with each other, but if you integrate them against a test function of x and y, you get nice functions on the cotangent bundle whose Poisson bracket is well-defined. This is just a quick way to say that. Okay. Now, it turns out there are 10 Einstein equations. G mu nu equals 0 is Einstein's equations. Mu and nu go from 1 to 4, but it's a symmetric tensor. So you get 4 choose 2. Sorry. 4 choose 2. How does that come up? No, it's not anti-symmetric. It's symmetric, so you get 10 independent entries of G mu nu. It's not 4 choose. Yeah, whatever. 10, okay? It's a number of, dimension of the space of symmetric 4x4 matrices. I can just see them there, those 10, okay? So, okay, I was getting too fancy here, okay. So there are 10 Einstein equations, but it turns out that 4 of them are actually constraints on initial data for Einstein's equations. So the initial data that we're talking about are these guys Q and P. Or more precisely, they're the metric on spacetime and the extrinsic curvature of space-time as embedded. Sorry, the metric on space and the extrinsic curvature of space as embedded in space-time. Those are Q and P. You should think of P as being a whole lot like the time derivative of the metric. It's basically some function of the time derivative of the metric. So those are the typical sort of initial data you'd want to have as you try to solve a second-order differential equation. Yeah? Yeah, that's right. Yeah, there's some. The formula is a little more complicated than that, but it basically captures the information about the time derivative of the metric as you push that surface forwards along that normal vector. Yeah, there's some formula relating the two, which is pretty simple. So Einstein's equations are a second-order differential equation in terms of the metric, so you'd expect to need the metric and its first time derivative as initial data, but the tricky part is that there are constraints. And these constraints are the components of Einstein's equations that have a 0 in them, that is the time index. I'm going 0, 1, 2, 3 for time and the 3 space coordinates. That's my indices here. And 3 of them, that is the G0I equals 0 equations, where I goes from 1 to 3, those are called the diffeomorphism constraint. The fourth one is called the Hamiltonian constraint. These diffeomorphism constraint ones are basically, if you work it out, if you work out what G0I is, it turns out to basically be a covariant derivative of this P field contracted in this way that I've shown. So basically, it's telling you stuff about the derivative in the spatial directions of the extrinsic curvature. So it's basically saying that the divergence of this P field is 0. And now I've told you that constraints, that is functions on a Poisson manifold, if you're lucky, they will generate flows. So you should ask, what flows do these constraints generate? There are lots of these constraints, not only because I goes from 1 to 3, but also because we can evaluate we can take this and smear it against any test function and get something 0. More precisely, smear it against the test vector field. So when we get to get a lot of constraints out of this equation, what we do is we take some vector field V super I on space, multiply it by G0I, sum over these repeated indices, and integrate it using the volume form on space from the metric. So these are a whole bunch of things that have to be 0, and one can ask, what flows do they generate? Well, they just generate the action of diffeomorphisms on T star of met S. So here, this is the connected component of the diffeomorphism group of space. It acts naturally on metrics on space, and therefore on the cotangent bundle of met S. And it turns out that group action is generated by these functions on the phase space. So that's why this is called the diffeomorphism constraint. So it's talking about diffeomorphisms of space. The Hamiltonian constraint is really talking about diffeomorphisms that push our spatial surface forwards in time. So it's sort of a similar kind of thing. The formula for it is a lot more complicated, and this constraint is always the killer, the thing that kills you in any attempt to try to quantize gravity. Not only because it's more complicated in its expression, but also because it's mathematically more subtle. It's generating not exactly a group action, but I will sort of weasel around that in this manner here. I'll say it generates the action of time translation in the n direction. N was this unit normal to our space-like surface. So what I mean by that is if we take this G00, multiply it by any function on space, and integrate it, we get this quantity, which is a function on T star of met S, and we can ask, what does that generate? And it generates a certain flow, which corresponds to what you get if you took a solution of Einstein's equation and pushed it forwards in time using this vector field F times the normal vector field. So the point is, in general relativity, everything is very wiggly. So you're not only interested in being able to evolve things forwards in time, pushing them at the same rate everywhere across your space, that is, pushing them forwards in time by the vector field n. You might want to evolve in time a little bit here, but more over here. So you like to have this freedom, in fact, to flow time forwards at different rates at different points, and so we actually are, it's actually sort of a feature that we can find constraints which easily generate any of those kinds of time evolution. Let's see, maybe I have here I've got a picture here that makes this hopefully more clear what's going on here. So what I'm getting at is that in general relativity, the dynamics, that is time evolution, is generated by constraints. So here's a picture of our surface S. We have this normal vector field n. We could multiply by any function on S and get this not necessarily unit normal vector field f times n. We could also take any vector field on space, tangent vector field on space, v, and we can add those two and get fn plus v. And we could ask what happens as I start pushing this surface S forwards in time in the direction fn plus v. Well, at this given moment in time, we'll have some particular metric and some particular extrinsic curvature. But as I solve Einstein's equations and then push this forwards, the metric and extrinsic curvature will change as I push the surface forwards. So we're really getting a flow on this space T star of met S. That's the space where the metrics and extrinsic curvatures live. And that flow on T star of met S is generated by this particular function on T star of met S. You just take the various components of Einstein's equation, G0I, and multiply them by this vector field, and the 0, 0 component, and multiply them by F. So here's a formula for what we get when we take these constraints and smear them against the most general possible things, a function in this case and a vector field in this case. And here's a geometrical picture of what they're generating. So that's what those constraints mean. But the interesting thing,
Why do you call it time evolution?
it's some evolution, yeah. I mean, it's the closest thing there is to time evolution in general relativity. So if you know what's going on now, you want to know what's going on later, where later could be any wiggly slice up there, this is what you got to do to figure that out. Let's see. Let me whiz along. No. So that's another reason why Dennis's question was right. Yeah, we could just push things solely along in the spatial directions, and this also covers that. That's true.
Pushing so that already pushing such a way to keep the solution, sharpen the solution, or right now you're just pushing it away.
We can push any old way, and it will turn out that if the initial data, that is the point in T star of met S, was initial data for some solution, then it will continue to be initial data for some solution. So remember how Poisson reduction worked. You have some constraint, it picks out a submanifold. That constraint function also generates a flow, but that flow will, I may not have said this, I should have said it, that flow will map that submanifold to itself. So that's saying that if we started out satisfying that these two guys were equal to 0, then this flow will preserve that condition. And even better than that, not so obviously a consequence of that, what we'll get if we assemble all these slices together and figure out what metric we get on space-time, what we'll get is a solution of Einstein's equations.
So can you connect these last paragraphs with the picture you had talked about?
Yeah, that's,
The summary.
yep, that's what I'm going to do. Here it is. So if you're trying to describe the space of solutions of Einstein's equations, you can start out with a cotangent bundle of the space of metrics on our three-manifold, Riemannian metrics on our three-manifold, and we can do Poisson reduction to it twice to get a space of solutions of Einstein's equation modulo diffeomorphisms and make that into something like a Poisson manifold. An open dense set of it will be a manifold. So you can first consider the diffeomorphism constraint. So you pick out a submanifold and then you mod out by the action that those constraints generate, which is the diffeomorphism group action. And so you get this the cotangent bundle of the space of metrics modulo diffeomorphisms. So that's a somewhat nasty object. It's not a manifold, but if you work with appropriate Sobolev spaces, it will be a manifold. In fact, a manifold that looks locally like a Hilbert space on an open dense set, as long as you're away from the metrics that have extra symmetry. And then you can again do Poisson reduction using the Hamiltonian constraint this time, and you get the space of solutions of Einstein's equations modulo diffeomorphisms. You notice there's some technical caveats there.
The first thing is here,
Right. This is why, so Dennis is saying the first thing is very clear, but the second thing is not. That is exactly why quantum gravity is hard. We understand this stuff pretty well at the classical level, and we understand it well enough to quantize all that now. But this step here is where things get murky because we don't have a very clear picture of this. So no, I can't give you a clear picture of that.
Where is the constraint surface in the first step?
The constraint surface is the first step is all those pairs satisfying G0I equals 0. So the surface where...
Not all of these are, but that's
No. What this process here, remember, it's always picking out a submanifold and then modding out by a flow. So that we pick out a submanifold of this. Let's see. No, but this is still true nonetheless. Yeah. So it's not. Yeah, I think that's true. Now you're getting me nervous. I think it's true. Yeah. But you still get a space that looks like this. Now I have to think about that. Now you're getting me nervous. Yeah, that's true. Let's see, I better stop soon, but not yet. So here's why it's so hard to quantize gravity from this point of view. So we have the diffeomorphism constraint and the Hamiltonian constraint at the classical level. These arrows are not maps. They are processes which turn the space into some other space, not maps between spaces. So these are two Poisson reduction steps. If you wanted to fill in the picture by also talking about the quantum situation, you get this diagram like this. You would like to have this initial Hilbert space, this kinematical Hilbert space, be L2 of the space of metrics. Here, L2 of the space of metrics modulo diffeomorphisms.
I think on the previous slide, it's a metric modulo.
The first.
You had T star as a it's metric modulo. It's both. Is that what you have now?
Here, no. Remember, you don't do L2 of the cotangent bundle when you're quantizing. You do L2 of the thing it's the cotangent bundle of, right? So there shouldn't be a T star in here, but there should be a T star here. This is our classical phase space. Metrics modulo diffeomorphisms is the classical configuration space, and L2 of that you would hope would be the Hilbert space of the quantum system. And so here, so the problem is, all these question marks are various things that no one knows the answer to. L2 of this infinite dimensional manifold. What the heck does that mean? What measure are you using? No one knows. L2 of this, we don't know. How do you turn the constraints over here into operators over here so that you can find the kernel of those operators if you're trying to go down from here to here? No one knows. Similarly, no one knows how to do that. And so, and also no one knows a direct step to quantize from here and get a Hilbert space here. So obviously, we don't know if these diagrams commute. We don't even know what half the arrows are. Okay, but if you were able to do it one way or the other, then you can then start worrying about whether the process commuted. So those are the mathematical difficulties, and one reason why it's hard to find these vertical arrows here on the right-hand side is that you would try to be turning gadgets like this into operators. Square root of the determinant of a metric is a horrible thing when you're trying to do that. And then finally, even if you have succeeded in doing this, you'd still be confused because the states in this final Hilbert space would be describing diffeomorphism invariant information about the quantum geometry of space-time. So it would still be hard to extract information about dynamics. So those are the problems. And let me just... Dynamics means we want to know what's going to happen. Physics is about figuring out what's going to happen. No, it's not on the symbols that's on the slide. See, it's hidden. Oh, you didn't read it. So in other words, in situations, see, there's a big difference between general relativity and all of other theories, which is why it's such a nightmare to try to understand how to combine it with quantum mechanics. In all sorts of other theories, like a particle on a line or the standard model, time translation acts on the space of physical states, classically or quantum mechanically. And dynamics means that group action. Here, there isn't, by the time you get down to this step of having imposed the Hamiltonian constraint, there isn't anything that you could dream of calling that group action anymore. So you can't simply say, I'm going to take a state of quantum gravity, evolve it in time for 10 seconds, and see what state it becomes. When you're down here, there's no such way to do that. There are no actions around that would let you do that. So that's what I mean by saying that dynamics is hidden and that there's this problem of time.
How do you ever get a physical theory out of it?
There's been a lot of work on trying to understand that. I believe you can, and you have to basically figure out how to ask questions about the world without ever explicitly mentioning time. You have to ask something more like this. If it rains tomorrow, will we have a picnic? See, that's the kind of question that you can ask without ever mentioning time. It's relating to physical observables, but never mentioning this imaginary t coordinate. So you have to... Okay. When we have a picnic, will we be today? No, when we have a picnic, will we be happy? Yeah, so I understand that it's a difficult business to phrase things about the world that never mention. You're allowed to do stuff like this. You're allowed to say, tomorrow, as shown by my watch. That's a physical object. So you can say things like that. You can say, in a diffeomorphism invariant manner, you can say, when the chime rings 12, will we all be happily eating our picnic? The answer is no, because we're running over time here. But that's never mentioning the coordinate time. That's just mentioning a physical object, the clock. And that's what you can do. That's what you're allowed to do. There's a huge amount that's been written about this. It's a really fascinating and knotty issue. And all approaches to quantum gravity that don't face up to that sooner or later are eventually going to have to face, are going to eventually get stuck, because it's really an important feature of the world. That it doesn't come with coordinates. It doesn't come with coordinates drawn on it. So one route to progress, is to describe general relativity using some new variables so that you're working with a cotangent bundle of a space of connections. I'll show you how that works time after next time. And then it turns out that you can define L2 of that space of connections. More precisely, you can define L2 of a certain completion of it. And then we can try this whole story again and get farther. We have to make the story a little bit more elaborate. We start out with a cotangent bundle space of connections, then modulo gauge transformations, then the diffeomorphism constraint, then the Hamiltonian constraint. We know in this formalism what the first three Hilbert spaces are quite well. Pretty much everyone in the field agrees with those. In other words, we have a definition of L2 of the space of connections that works in this formalism. And also the space of connections modulo gauge transformations, suitably completed. We even know how to mod out by diffeomorphisms. As you might expect, the difficulties aren't gone. There are candidates for operators on this Hilbert space whose kernel would define the physical Hilbert space, the space of states that you're actually after. However, people are busy arguing about whether those candidates are right. What Ashtekar will talk about is one recent calculation having to do with the Big Bang, which actually makes use of one of these candidates and gets some answer for some physical questions, which is a way of testing whether you're doing things right. But basically, by switching from working with metrics to working with connections, we seem to be able to get further in this program here. And so that's what I'll talk about in the remaining talks. Okay, thanks.